presented by Caltech.
All right, so today's discussion is going to be focused on the idea of interference. And the word might sound pretty interfering with your minds, but it's all about learning how to add. Okay? It's just about adding numbers in a more general way than just 2 plus 2. That reminds me of a joke. My father, when I was starting to do physics back in my high school days, taking interest in relativity and quantum mechanics and little nerd boy running around like and stuff. He used to say, what's all this physics and stuff, I come from a family, no one is a scientist, like no one is close to science by far. They're either doctors or or businessmen. That's what we do. So he's like, what's all this physics and stuff, Come join me, son, I'll teach you how to make 2 plus 2 5. That's the crux of life. Where I'm like, nah, I'm happy with simple interference addition. So I'll focus on the Young's Double Slit Experiment, which I hope all of you have seen before. Have you all had the things before? High school, physics 1? Okay, good. Last year. Alright, so what we do is we try and discuss in a little more detail than usual. We won't just say the fact, okay, whenever the phase difference is a multiple of 2m pi, it's a maxima. Whenever it's 2m plus 1 pi, it's a minima. No. We'll solve for the physics which actually goes behind this and see some very nice subtleties in this setup, which no one really tells you in the first, idea for this double slit experiment, basically. So we talk about that. Hopefully that will be for the next 30-35 minutes, and then we'll see for the last 20 minutes we'll talk about something more historical, more interesting, at least more exciting. Okay, so the idea here is that it's all about superpositions, and this word might sound trivial to you by now. Just add things up. But that is at the crux of how physics works. Be it quantum mechanics, be it classical waves, superpositions are just very, very important. In quantum theory, they become even more important because you could have superpositions of classical states. I could be here and there. That addition becomes kind of bizarre in quantum theory and becomes real. So that's for next term. But every single kind of wave we know, be it light waves, gravitational waves, just any kinds of waves, spring waves, oscillation, sound, they would all interfere. Point being that two of them, when put together, they would add. And the point about superpositions is that when you add something, when you add x1 and x2, by this add I mean in the interference sense, so it's adding as an interference, it's just their sum, okay? Nature could have been different. Nature could have, I said, if I add things up, you must put together their squares maybe. Nature could have been different, but it isn't. It's just adding simple things up, okay? So we should thank nature for that. We used our exam problems. So we'll see what happens. So the setup is we have some screen with 2 slits, S1, S2, equally separated of some point called the origin. It's a random point called the origin. The actual screen is at a distance capital D away from my slit plane. The distance between these 2 slits is little d. And what I send in is a plane wave of maybe electromagnetic radiation, gravitational radiation, something. I send this in, and therefore I draw these as plane waves because at each of these slices, the phase of the wave is a constant. It's a locus of points for which the phase is fixed. Okay? And omega is the frequency, which is source dependent. The wave is propagating in. It hits this barricade. It has these 2 slits in there. Now we all know some of the light must pass through these 2 slits. It goes through. Now light from slit 1 and from S2, they would add up in different ways on the screen that we have here. Okay? But the first question is, if I have plane wavefronts coming in before the slit plane, this slit plane is actually perpendicular to the board. It's coming out towards us, this side. And these slits are long line slits in my setup here. You could have circular apertures, which I think Frank will discuss in class, but this is a line slit. Okay? So for line slits, what kind of wavefronts, what kind of light wavefronts do you expect in this region in between the slits and the screen? How should the wavefronts look like? This is crucial to what's going to happen today, so this needs to be understood very, very in an important sense. Yes? I mean horizontal as in passing through?
Yeah.
So the light propagates in a straight line, at least non-quantum mechanically. It's the direction of propagation could be some straight line, but the wave front, the locus of points which has the same phase, how would that look like?
It's still like semicircular.
Okay, getting close. We've seen this picture of semicircles like
Yeah.
popping out, right? So we say, the wave fronts look like that. Maybe some other color for this one. But the light, as you were mentioning, travels in a straight line. That's
Yeah.
good. But it's not really circular, semicircular, it's not. Think about this. The slit is actually a line slit. And it's almost infinitely long. So every point on the slit acts as a sort of secondary wavelets. So the light comes in, hits the slit, every point in slit 1 emits its own circular radiation, and when they all add up, symmetry tells you it must be cylindrical. So the wavefront for this line slit is a cylindrical wavefront, like a semi-cylindrical wavefront in that sense. Okay. Had it been a single point, it would have been spherical. But this is not a point. This is a line slit. Just like if you have a speaker which looks like a line, which is a long line, the way the sound propagates is, in cylindrical wavefronts. Okay. So first thing that is important today is that the wavefronts are cylindrical. This has like 3 parts. Part 1 is like setting this whole thing up, understanding what the basics go into it. Part 2 is the math, the adding part, and part 3 is plotting it up, like see how it looks like. Okay. So, yes, cylindrical wavefronts. What's special about them? Let's go back for a second. For the case of plane waves, the amplitude of this wave, that we call this script A, the amplitude, this amplitude doesn't depend on where you are. I could be on the first green line, or the last green line, or just by the slit. The amplitude is not changing. It's a simple sine oscillation, or cosine oscillation. It just goes up and down with the same amplitude. For cylindrical waves, however, the amplitude falls with distance. Again, think intuition. If I have this long speaker, which looks like a line, the further away you are, the less loud it is. A single point also, which has spherical wavefronts, the amplitude falls down with distance, because if you're further away, you hear me less. Definitely to say further away from me. So that's how these things move. But plane waves, they have the same amplitude wherever you might want to be. So how does the amplitude of a cylindrical wavefront die down with distance? Any guesses? That as a function of r, or distance, how should the amplitude decrease from its initial, whatever the value might be? Yeah.
1r².
It's a good guess. You're close in power, but not quite. So let's see how it looks like. Look at the wave equation. It's not obvious. It's not an obvious answer. The wave equation that I have is my physics 2A wave equation for either electromagnetic radiation or sound or whatever. And the equation looks like Laplacian acting on the oscillation. So let me call the oscillation as psi. Psi is not the quantum wave function. Psi is just what is oscillating. And if this is Young's double slit experiment oscillating, it is just light waves, and therefore psi is the electric field or the magnetic field. Okay, psi is a placeholder for what is really oscillating. What's the wave equation? This equals 1 over the speed squared times partial squared psi partial t squared. That's my physics 2A wave equation. Second time derivative equals speed squared times the space derivatives. We all see that before? Okay. Okay, now here's the kick. In cylindrical coordinates, because I'm looking at a cylindrical symmetric system with lines and then cylindrical wavefronts. So for cylindrical coordinates, the Laplacian looks as follows. It looks like 1 over r squared partial square psi partial r squared plus 1 over r. Actually, hold on. Yeah, partial psi partial r. Is there a 1 over r squared here? No. So this is, give me 1 second. This is, yeah, okay. So this is how it looks like, the Laplacian, which was just partial x squared, partial y squared in like Cartesian coordinates. It has the double derivative, and r is the cylindrical radial distance, and also has a 1 over r and a first derivative term. It's just coordinate changes. It's not new physics. It's just going from xy to the cylindrical distance r and the angle theta. Okay? Just change of coordinates. You can do this on your own time. You can verify this. Now it turns out when you plug this back in here and you're looking for solutions far away. So I'm going to be working with the far field limit. And the far field limit is basically saying that my screen is really far away from my slits. Okay? So r is much, much larger than 1 in the right units, in some units. It's looking really, really far off. In my setup, it says that capital D, the distance between the slits and the screen, is much, much more than the distance between the two slits. Okay? So this is the far field limit. And I'm claiming that the solution in the far field limit of the wave equation in cylindrical coordinates is as follows. Psi rt goes as some amplitude constant over square root r e to the I kr minus r. R is the distance from the source radially measured outwards in a cylindrical sense. Okay? So the amplitude has a 1 over square root r dependence. It falls down not as 1 over r, but as 1 over square root r. Okay? Were it a point source and a spherical wavefront, it would go down as 1 over r. So in plane waves, it's constant, the amplitude. Cylindrical, it's 1 over square root r, and for spherical waves, it's 1 over r. Question?
What's the difference between cursive R and non-cursive R?
There is no difference. I just don't know how to write. Yeah. I need to get my r's straight. So yeah, so this r equals this r. Honestly, there is a book by David J. Griffiths on electromagnetism, and maybe even quantum mechanics does this, but he uses this regular r and the script r in different notation. And I thought I would grow up and learn how to do this, but I just never did. So please forgive me for that. Same r. But are you all okay with the fact that the amplitude goes down with distance? So as I'm going from the slits to the screen, the amplitude is falling down. Okay? All right. So that's good. Looking at the far field. All right, so what happens? Now, I have these cylindrical wavefronts propagating. I choose an arbitrary point on the screen. Okay. It's some point on the screen. Let's call this direction as y, because it's in the y. Let's say this point is at a distance y from the x-axis in the y direction. And then look at what happens from light from S1, light from S2, when it hits the point T, which is at distance of y. Of course, y is variable. I can solve for some y, holds for every point on the screen. So now, as you were saying, the light propagation is in a straight line, at least in geometrical optics. Quantum optics is slightly different. Okay. So light reaches here in straight lines, but the wavefronts are cylindrical. The distance from S1 to point P is R1. Again, this R is just the R. There's no script, no other R, and this is R2. Okay. And let me call this angle between point P and the origin O as angle theta. So there's some drawing to be done. Once we're done with this should not be that far. So y, you could label the point by either the distance y or the angle theta. Okay. All right. All okay with this stuff? Does that make sense? Okay. Now I want to make two claims here. The first claim is that, we should continue here. The first claim is that the two distances, R1 and R2, are different. We all see that? Because the slits are different, therefore R1 and R2 are different. So R2 minus R1 is non-zero. So they're different in the additive sense. If you add or subtract them, there is a non-zero value to it. And why is this important? Because this is the path difference. This is, that's what's delta R. So delta R is R2 minus R1. This is the path difference between the two rays of light from the two slits. The phase difference, also called the optical path, sometimes in some literature, it's called the optical path. That is the, so if you look at a wave, the wave goes like I kr minus omega t. And in the I, it's e to the I times the phase of the wave, right? So the spatial part of the phase, or the spatial part of the phase is just k times r. Okay. If you move a distance r, depending on what k is, you pick up a phase k times r. Right? Yeah. So the phase difference, phi, is k times delta r. And k is just 2 pi over the wavelength, and delta r is r2 minus r1. You might ask, if I'm looking really, really far away, r2 is almost r1. But that difference is still important because if r2 minus r1 is small, lambda could also be small. So if both lambda and the delta r are small, the phase difference is pretty large. It could be pi, 2 pi, some like non-trivial number. So delta r is additively important. The difference is important. Okay? And this is the phase difference. My second claim is that R2 and R1 are multiplicatively the same. They are additively different. They are different in that. But they are multiplicatively the same. What do I mean by that? By that I mean R2 over R1 is approximately 1. I'm not going to look into account for differences which are in the ratio or in the multiplication between R2 and R1. How can I prove that to you? Look at delta R again from the difference. It's R2 minus R1. I can write down delta R over R1 as R2 over R1 minus 1. Okay? Then look at my claim now. So R2 over R1 is equal to 1 plus delta R over R1. You all okay with that? Now, here's the claim. The claim is that delta R would always be less than little d. Have a look. Delta R, which is the difference between the path lengths of these two light rays, has to always be less than the distance between slits. Why? Because it will only be maximized when the two light rays go vertically up, and then the difference is just d. Else it's always smaller. We all see that? Everyone? So delta R is less than d. And the fact that R1 is always more than capital D, or equal to. The distance from the slit to the screen. If it goes straight, it's capital D. If it is any other angle, it's more than capital D. Okay, what does that do anything here? So delta R is less than little d, R1 is more than capital D. Hence, R2 over R1 is less than 1 plus little d over capital D. and I am in the far field limit. And therefore, I can neglect the d over d term, and R2 over R1 is multiplicatively the same. Additively not, because the phase differences matter, but multiplicatively, which said differently is that from the point of view of this point, P, S1 and S2 are equidistant. But the phase difference, the distance separation, is important. Question?
So why can't we say that like delta r is less than or equal to like little d?
You can say that.
We can.
So yeah, I should have it called. Yeah, thanks. Okay, so that was the physics part of things. So if you're not comfortable here, please ask me. Because you're okay with this stuff. The rest is just math. You're just adding stuff out.
Why does R2 over R1 being less than 1 prove that they're multiplicatively the same?
I have bound this by this number. Okay. And this thing is much, much less than 1. So whatever the difference away from 1 is, so R2 over R1 is not always 1. There is some difference because they are different lengths. What I'm saying is that the difference is, it's 1 plus a very, very small number. And therefore, multiplicatively, this thing could be ignored. It's like saying, if I have two numbers, A over B, which were slightly different, you could write the difference down as 1 plus some number. And that number is very, very small, then you can just say it's almost 1. That's what I'm doing. You see that? Okay. Any other questions? This wasn't the most obvious jump from, I've seen this before, and then this comes into the picture. So if any questions, please ask. All with me? Okay. All right. So we have this. All right. Now let's just add. Now it's a matter of a little math and to get the final answers. And I should also, what's delta R in terms of little d and theta? D sine theta. D, you can drop a perpendicular. You can say, okay, do a little trick. You've seen this before. Okay. Everyone sees this? Just a little simple right angle triangle. This is delta D. This distance here, this one here is delta R. So if this is theta, this is theta 2, theta and this is theta as well, and therefore it's just D sine theta is. All right, so at the point P, so the total electric field, let's say, or total psi, I'm going to be thinking about light now. So the psi is the electric field. The total electric field, E tot, at the point P is E1 from the first slit at point P plus E2 from the second slit and on. Add them up. Okay. How does the electric field oscillation look like at the point P from the slit 1? There is some amplitude, but it's falling with the distance. Okay? So this is some constant over square root R1 from the cylindrical idea that it has a decreasing amplitude. Times e to the I kr minus omega t and R1. That's the oscillation at the point P from the slit 1, traveling a distance R1, amplitude went down by a factor of 1 over square root R1. From the second slit, unimaginatively, it's just the same constant over square root R2, e to the I k R2 minus omega t. The same omega, because omega is a source-dependent thing. I'm telling in the same plane wave, hence both slit 1, slit 2 have the same frequency. Okay. All right. Now, since I argued that R1 and R2 are multiplicatively the same, hence A over square root R1 is A over square root R2. we all see that. If R2 is almost R1 multiplicatively, so this follows from R2 being approximately R1 to the multiplicative idea, and hence A over square root is equal to A over square root. And let me call this as A over square root R. Okay. I'm dropping the label 1 or 2 because they are the same. All that matters is the distance R from maybe the center, because R1, R2, and the yellow line, they're all approximately the same multiplicatively in the far field limit. So I can write this down as A over square root R, pull that out, and look at the following. I'm going to play a little trick. Have a look at this. E to the I K R1 plus R2 over 2 minus omega t. So that's what I want. That's what I want. Let me put this down first. E to the I K R1 minus R2 over 2 plus e to the minus k minus ik R1 minus R2. Can we convince ourselves by looking at this that I just factorize, so the averages were both the same, I pulled that out by the multiplicative idea. The exponentials, I pulled out the average distance R1 plus R2 over 2. And therefore I could get the differences inside. Do we all see that if I multiply this together, I get back what I had before? You all see it? Okay? Alright, so I have my delta R's, R1 minus R2, and I have e to the I k something plus e to the minus I k, that same thing. What does that remind you of? Yes?
Wait, sorry, I don't see why the average is, like, gives you the difference inside the
Just multiply this with this. What do you get? You have e to the I k. So when you multiply, the arguments add up. The minus omega t is just the same on both sides. When you add the first term, it's ik r1 minus r2 over 2 plus r1 plus r2 over 2. So the r2 part goes away. R1 over 2 plus R1 over 2 is R1. So it's ik R1. And therefore I have ik R1 minus omega t. And the second term with a minus, the R1 cancels and the R2s combine to give you R2, and then you get this. Alright, so I have e to the something, e to the minus something. What does that remind you of? E to the I theta, it's not called theta, I have a theta somewhere else. E to the I alpha, e to the minus I alpha. What's that? 2 cosine, right? It's 2 cos alpha. So what do I have here? I have a over square root r twice cosine of the angle k r1 minus r2 over 2 times e to the I k, the average r1 plus r2 over 2 minus omega t. Okay? Okay, this is getting a little tedious, but we're going to see what happens now. We all see this? Okay? Now we're done. The exponential part outside is just a wave. Right? It's an oscillation. And if R2 is R1 multiplicatively, it's just like e to the I k r minus omega t. This part is the oscillatory part of my solution. And whatever goes with the oscillation is the amplitude. Right? So my amplitude of the total amplitude, A total, at the point P, okay, is twice A over square root R. Let me call this, that's fine. Cosine K times delta R over 2. Delta R is d sine theta, so K d sine theta over 2. That's the total amplitude at the point P. So just this square bracket term here, in red now, that's my total amplitude at the point P A is that constant, 1 over square root drop from cylindrical wavefronts, and the phases have added up in this way. Okay? What does that say? All right, so let's find one thing first. What's the A total at the point P equals 0? The point that is here. This is the point P equals 0 or theta equals 0. If you want me to call this theta, I'm going to call this theta equals 0. This is the point on the screen labeled by theta. What happens when theta is 0? Okay, I need a 0, cos of 0 is 1. So the amplitude, total amplitude at the middle point is 2a over square root r, which is just this piece. Okay? And therefore what I have a total at the point theta on the screen as a ratio with a total at the point 0, the middle one. I want to compare amplitudes in the multiplicative sense, like how much I'm increasing in amplitude. This is just cos, there's something wrong. I wanted something else as well. Yeah, okay, sorry. Look at this. This r also depends on theta. Depending on what point I am at, the r will change. Okay? So this r depends on theta. So when I have theta equals 0, what's r when theta equals 0? D. Okay? So this thing, hold on, I'm confused. I'm missing something very trivial here. Square root r that we have there. Yeah, okay, I got it. Sorry about it. Let's go step by step. This is square root r0, square root r theta. When I divide this out, the 2a cancels off. So this whole thing is of course not the same. There's a difference of theta. When I divide them out, I have square root r at theta 0 over square root r at theta times cosine kt sine theta over 2. Okay, yeah, I got this now. Under control. Do we all see that? No? Be bored. The ratio of the total amplitudes at some point theta and the point 0 is the 2a part went away. It's the r at 0 over r at theta, the square root, times cos theta. All with me? Sorry, that went a little off, but yes.
Why do you care about taking the ratios?
Because the actual numbers would not be so important, because the screen would detect some intensity, some amplitude. And I want to think about whatever is happening here, in what ratios of it is my pattern going to look like. Because this A that I have here, it could be some constant depending on initial conditions. I want to get rid of that. I want to just look at the pattern by itself, not referring to an incoming initial constant amplitude. Like, even if I change this A now, the pattern's ratio doesn't change. Okay? That's what I'm trying to achieve here. So I get the ratio of the total amplitudes at this point. And now look at this. What's square root r0 over square root r theta? Let's make a quick drawing again. Slits. This is D, screen. This point is theta. This point theta equals 0. Right? So when r is, when theta is 0, your distance is just this distance here. And for anything else, this is basically just square root cos theta. Do we all see that? Just a simple like trick with that diagram, what the distance to center point is versus some other point is just a matter of a cosine shift, right? So once I have that, and then the intensities. So the intensity at the screen, I total, at angle theta over I total at angle 0, the center point, it goes as the square of the amplitude. The energy or the intensity is half k a squared amplitude squared. So this is cos theta, the square went away, times cos squared kd sin theta over 2. That's the actual pattern on the screen that you look at. Okay? Before, you've always seen just this part, cos squared kd sin theta over 2. This additional cos comes in, we worked all of this for that additional cos basically. And this comes in because of cylindrical wavefront nature of my waves. Okay? So let's write this down in terms of y and d's and stuff. So what's cos theta? Cos theta is d over r. So this is d over r. And I can write down r as square root capital D squared plus y squared square root, Pythagoras theorem. So this is square root d squared plus y squared. That's cos theta times cosine. K is 2 pi over lambda. The 2 goes away, it's pi over lambda. And sine theta is y divided by square root y squared plus d squared. Cosine squared. Yes. Okay? That's a function of y on the screen. Exactly just in y now. And now if I plot this out, here's where the good stuff happens. So if I make a plot of the intensity I total at theta over I total at 0 as a function of y. Okay, if I look up or I look down. Now the case for which d is much less than lambda. Do I have numbers that I want to use here? Not quite, not quite. I also have d floating here, it's kd sin theta. Okay. So when d is much less than lambda, the phase difference, d over lambda, is very small. Even if you change y a lot, the phase difference in the cosine squared term won't change as much. So only this piece, the cos theta piece, dominates. And the pattern is like this. This is just the cos, this is just the d over square root d squared plus y squared curve. The cos squared piece is not changing too much because little d is much less than lambda. As a function of y, the phase is not changing at all. So here is the claim that people make. That when d is much less than lambda, you don't see any interference pattern because along the y, there isn't much phase change happening. It looks like a single slit on the slit plane, and you just notice a single pattern on the screen, which is not interference by any means. On the other hand, when I have d is order lambda or more, then the phase difference becomes important. Then you have that same envelope, the red one, and within it you have a bunch of oscillations. Okay. Point being that the total intensity doesn't just depend on the phase difference, also on where you are. And to kind of close this discussion a little bit, I work in the far field limit. add on to that the small angle approximation. I mean, theta is much, much less than 1. So I'm looking at points near to the axis. I'm looking at points really, really close here. For small angles, when theta is much, much less than 1, cos theta is almost 1. So this envelope doesn't really make a difference. If I look in really, really close here, it looks like a simple interference pattern. In that case, it looks like what you're used to from high school, from physics 1. This is, again, the I total over I at 0 as a function of y for small angles. Okay? But for the full picture, there is also this drop because of the cylindrical wavefronts. Only when you look far away and too close to the screen, only then do you recover your old pattern from high school and physics 1. But the actual pattern depends on whether the slit distance, how does it play with the wavelength. If it's really, really small, no phase change, a single slit. If it's ordered, the wavelength or more, then you have a much more interesting interference pattern. Is that good? That was like a lot happened in a short time, but idea being that it's much more rich than just that single cos squared pattern that people show you in early classes. Yes?
So I have a general question about interference. So I was reading that if you have some sort of constructive or destructive interference, there has to be like a corresponding, like if you have two perfectly constructive waves, like they're in phase, and somewhere else you also have to have some destruction, otherwise you would have like a non-conservation of energy. But I don't see how that makes sense if you have like two waves that are perfectly in phase or perfectly out of phase. Where is that other part being lost or gained to make up for?
So if you have something completely in sync, right? If I have a wave like that, and I have the same wave, it's completely in sync with it, they just add up. So the amplitude went up, and the energy also is more because the energy of the two things is like the addition of the two energies. So there is no destructive interference anywhere here. Every point is just adding it up in the same way that the first thing is providing you. So I don't think it's true that if you have two waves, there's got to be destructive interference somewhere. Doesn't have to be true. In the general sense that you just like add the same wave up again. Everywhere just adds up. So I don't think that claim is quite true.
Okay, then where is the corresponding energy loss? Because
There is no energy loss here. It's all energy conserved. You're just adding waves.
Oh, because if they both had like
They have amplitude A and A.
just have
So things like 2A or something, the energy is the same energy that you have. Energy is not lost in interference. It's just the actual, what happens in reality is just you see the actual sum of the two. We're just breaking it up into individual, which actually can understand at each level of the sign wave.
Okay, so then if you had destructive interference and if you have two waves that are they have the same amplitude, they both have some energy x, then if they perfectly destructively interfere, then now you have a wave with no amplitude.
But there are places where there is more energy. Okay, then maybe what's confusing is the fact that energy is not contained at individual points. Waves don't carry energy at every point, like this point has this energy. The wave as a whole propagates energy. Okay? So each wave has some energy. This has some energy, they just add up in the regular sense. The destructive interference is not altering the energy pattern because even though the amplitudes might look different, there might be nodes, anti-nodes, but each point has no energy to be associated with it. Energy is of a wave. It's not of individual points on the wave. Okay? You see what I'm saying? Okay. Good. So, all right, that's interference. And if you just like look at this thing, this is just the same pattern from before. Let's spend the last 10 minutes talking about something more different and something a little more interesting. So, I want to go back to July 1947. In the small town of Roswell in New Mexico, a farmer or some hardware person on a ranch, he saw these big discs like falling from the sky. Okay? And then the Air Force, the Roswell Army Air Force Base, the people swoop in, they collect the debris, and they have a newspaper article next stating that the RAAF, the Roswell Army Air Force, they have recovered the flying discs. So they recovered something called the flying discs. There was a big hue and cry, like, what are these discs? What are they huge? And the next day, after this paper clipping came out, the government took this paper clipping back. They retracted that information piece and said that the debris was just a weather balloon. That's what they said. Okay? And this became the famous Roswell Conspiracy of 1947. And it haunts our imagination still today about UFOs in Roswell. They were flying saucers, they were flying discs, and the government had to cover up like what they were up to. So that's like one thing which happened. They just said, fine, these were nothing fancy, just a regular experiment with weather balloons. But they were not weather balloons. They didn't look like weather balloons. People knew something was off. And this stayed with us for the longest time now. That's story number one. Story number two is World War II. Follow along. This is very interesting. Now, it's time of World War II. Not the same years, of course. And this American geophysicist and oceanographer, here, I think his name was Morris Ewing, I think. So this guy, Morris Ewing, people called him the Doc. This guy, he developed something called SOFAR spheres. SOFAR stands for something I tell you later what it stands for. But he made these things called SOFAR spheres. And they were given to every pilot in the Air Force. If the pilot was shot down and they landed on sea and somehow made it through in the crash, their emergency kits had a sphere. It was just a metal sphere. So if someone, the enemy, they got the sphere, it would just be a hollow thing. Nothing to notice. It's just a hollow metal sphere. They were instructed, the pilots, that if they crash, take the sphere, put it in water. The sphere would sink. And then within 2 days, rescue would come to pick them up. It's just a simple metal hollow sphere. No gadgetry, no weird electronics, nothing. 1940s. Just a metal hollow sphere. And rescue would come. So this is how people rescued our Air Force pilots back in the day. What really happened with the World War II story? When they drop it in water, water is very interesting in the sense that ocean water, when you go down, the temperature goes down or up? Down. It becomes cold as you go down. What about the pressure? Pressure goes up because there's much more water to push you down. And from your chemistry classes, we know that the speed of sound in water is proportional to the pressure of water and also proportional to the temperature, 1 over density. If you have a higher temperature, it travels faster. If you have lower temperature, it travels slower. You have more pressure, sound travels faster. Okay. So let's look at the ocean thing now. So this is the ocean surface, for example. As I go down into the sea or into the ocean, the pressure is increasing. So the speed is going up because of the pressure increase. But temperature is going down. So it's decreasing because of the temperature decrease. Okay? Turns out the way these numbers work out is that the speed keeps slowing down because of the temperature decrease, and then starts increasing again because of pressure increase. So the speed is fast on top. It gets slower. There is a layer for which the speed is slowest of sound, and then starts becoming fast again. So this decreases because of the temperature drop, and the pressure takes over, and it increases because the pressure is increasing. And in ocean water, this depth is about 1 kilometer, 0.6 miles. At this distance, the speed of sound is the slowest. Do we all see that? Okay. Now remember your high school physics or what Frank taught you yesterday about refraction. Light or any wave bends towards the medium of higher refractive index. Right? If I go from air to glass, it bends towards the normal. Okay? So the fast means it's a lower refractive index. So refractive index n is lower up here. Where the speed is slowest, refractive index is highest. Right? Because refractive index is, for light, it's, so the speed of light in a medium is c over the refractive index. So for higher refractive index, the speed is slower, right? So highest n, slowest speed, and then the n again starts going down. And light or wave, or any kind of wave, bends towards the normal, or bends towards the medium of slower speed. So any wave which I send around this slowest channel always bends towards the normal. It wants to go up, it's going to a medium of higher to lower, it bends towards the slower part. So it bends down, and then so on and so forth. So there is this sound channel in the ocean at 1 kilometer depth, where waves just get trapped. They can't escape. They try to go up, they bend towards the normal. Try to go down, they bend back up. And they travel along that channel. So this sound channel in the ocean was what Morris Ewing used. These SOFAR spheres were so designed that when you throw this in, this hollow metal sphere, it was heavier than water, it would sink. It would reach roughly 1 kilometer, where the pressure of water would crush it. And that crush would make a loud noise, like a loud firecracker noise. And that noise would travel along the sound channel in the ocean, undeterred, no losses, and goes through. And by the board, like by the shore of New Jersey and stuff, they had multiple microphones. They could hear this and triangulate where that thing is. Sweet stuff. That is sweet stuff. All right. Whales communicate through the sound channel in the ocean. So that's what happened with Morris Ewing in World War II. That's how they just rescued pilots. It's really cool. Story's not over yet. What about the atmosphere around us? This was water, right? And if you want to, so far stood for sound, fixing, and ranging. Okay, that's fine. Now in the atmosphere, if I look at the height in the atmosphere, the H, and this is, as you go up in the daytime, for example, the ground is hotter than the air up there. Okay? So the ground is, this is hotter, and as you go up, the air becomes cooler. Okay? That's how the atmosphere works. It's just usual stuff. So the refractive index is increasing as you go up. Okay? Speed is going down as you go up. And therefore, this is like real ground, this is the ground. If I send in a wave or a sound or something, this thing bends towards the normal, and sound always bends upwards when you have the ground being hotter than the upper atmosphere air. On the other hand, in the evenings, this is the daytime, usually the daytime. In the evenings, the ground cools much faster than the air. It's a solid, it's like IR radiation cools down. So this becomes cooler. The air is still pretty hot from the day. There's a temperature inversion which takes place, so just like some inversion. And now you have N increasing this way. So sounds or waves, they bend down. Okay? Notice this. So anything which in the morning it goes up like that, this thing just goes up. So one little cute fact, this always bending up, it creates this shadow region that faraway sounds never reach you. And therefore mornings are more quiet than evenings, because faraway sounds don't get to you. In the evening, there is no shadow region. Okay? And people realize that when they are at war, and this was noticed in Baghdad, that when they were fighting and stuff, they could hear a lot more gunshots in the evening than in the morning. And they're like, why is that? Are people like killing more in the evening? No, it was just that you could hear less in the morning. Okay? That's one fact of life. Now, if you keep going even higher in the atmosphere, okay? If you keep going even higher and higher, in the daytime, for example, the temperature was decreasing. So let me now plot as a function, this is the temperature of the atmosphere, as a function of the height in range, right? So as I was increasing height, the temperature was going down. It is, temperature is going down, okay? Now, above roughly 45,000 feet, heating from the ozone becomes important. The ozone absorbs a lot more UV radiation. And beyond this, ozone heating becomes important, and it starts warming up again. So it starts warming up. So I have regions of high temperatures. High temperatures means high speeds. So fast speed, temperature goes down, means slow speed, and then temperature goes up again. So fast speed. Compare this with the underwater case. Fast speed, a channel of lowest speed, and then fast again. In the atmosphere as well, fast speed, temperature decreases, reaches some altitude where you have the stratosphere, and then above that, temperature increases again, the speed goes faster. So at 45,000 feet, there is again a sound channel in the atmosphere. That sound sent around this channel just keep going without going out. It just traps the sound in that sound channel. And what the same guy, Morris Ewing, did in 1947 in Roswell, they used this sound channel in the upper atmosphere. It was a classified project called Project Mogul. They developed these huge microphones, which were shaped as discs. Huge microphones in the shape of discs. They would string it with weather balloons under them. So these weather balloons would all go up, and they would stay at the sound channel of 45,000 feet. A string of microphones, huge microphones. If you want a sense, this string of microphones, the length was half the length of the Eiffel Tower. It was that long, okay? And what the point was, that they wanted to detect Soviets' nuclear tests. Were they having any atomic tests going on in Soviet Russia at that time? And they were a closed society, so nothing really came out from information like regular channels. But if the Soviets, they blew up something in an atomic test, the plume or the sound or whatever, the detonation goes up into the atmosphere. There's some sound, there's some detonation that goes up. Sound which reaches here gets trapped in the sound channel. And it travels without any deterrence, any loss. It travels through the sound channel, and people here could pick it up that something happened at that point. And in August 1949, Project Mogul actually pinpointed the first Soviet atomic test because of these weather balloon flying disks. And one of them fell down, something malfunctioned, one of them fell down, and someone got what the thing was. So Project Mogul just used simple ideas of waves that all of us here understand. And they could detect. And yeah, I think that should sum it up. See you guys next week.